SwayamPrabha. Digital India. Educated India.
Welcome to the lecture. We were discussing about the method which we adopt to retrieve temperature of formation, temperature of the hydrothermal fluid that give rise to mineral deposits. We have already defined them. Fluid inclusions are tiny fluid filled cavities inside the host mineral, the mineral in which they occur. We call them as host mineral, and they are trapped during the primary growth of these minerals from the fluid, and they do also form within the minerals at any time later after their formation on healed cracks, healed fractures within the minerals, and we define them that they are fluid filled cavities. They are the aliquots of the mother liquor. Just to recapitulate, they display diverse shapes and sizes, and they do have a very good contrast, optical contrast with the host mineral in which they occur. And just for a recapitulation, this diagram represents the process in which the primary. So we call these inclusions, which are the part of the random 3-dimensional network, as the primary inclusions. The primary inclusions, and when we take a section and study under the microscope, we see these different inclusions getting focused at different planes, compared to the minerals which the fluid inclusions which are aligned on linear arrays, essentially the sections of the inclined fracture plane as it is shown here, and they are generally, if they traverse across many such grains of the host mineral, then we call them as the secondary inclusions. Since we talk about the fluid from which the minerals precipitate, we would generally be focusing on the characteristics of these primary fluid inclusions, but sometimes the hydrothermal fluid activity take place in a protracted manner, in episodic growth of the hydrothermal vein, like the one which is shown here, which makes even if we can establish a continuum of the fluid activity in different phases in giving rise to mineralizations in different generations, then the inclusions which occur as secondary inclusions in the older phase host grains could also give useful information to us. In this diagram, you can see that this is a typical example of the formation of hydrothermal veins in the normal crustal rocks in response to fractures, their fracture filling. So on this we see that the first generation of quartz were deposited on the fracture wall. Then there was a second phase of fracturing and fluid flow, and in which the second generation quartz precipitated from a fluid, and that fluid could eventually be trapped as secondary inclusions in the earlier generation quartz, and so on. So this diagram, which has been taken from Wilkinson 2001 from one of the research papers on hydrothermal deposits. So this gives us a very clear idea as to the fluid deposition process, formation of the hydrothermal veins in different generations, and the importance of the hydrothermal, the importance of the study of the fluid inclusions. Sometimes it may so happen, but if the fluid activity takes place with a very substantial time gap and with no relationship to the earlier stages of fluid activity, in that cases the secondary fluid inclusions will not of much use to us. Well, so getting into the fluid inclusion types, here it is shown on the diagram. It is a case where it is a liquid plus vapor, aqueous inclusion, aqueous liquid and aqueous vapor, which we can identify under the microscope from their optical properties. And this is a sketch of an aqueous inclusion which may occur with number of such mineral phases which are called as the daughter phases. We can see here like a halite. sodium chloride, this is potassium chloride, this is a calcium carbonate calcite, this is anhydrite. Even this can also happen a sulfide, a chalcopyrite, small grain of chalcopyrite also within the inclusion cavity. This represents the wall of the inclusion, which is essentially behaving as a closed system. This is just a case that compared to the situation here, where the fluid could be visualized as having very little concentration of the other dissolved species. As against that, this inclusion represents a fluid which was originally very briny or very concentrated in many dissolved solids, and which gave rise to this kind of mineral phases precipitating out in the inclusion cavity after the entrapment of this particular fluid. This is an example of a situation where an aqueous liquid and a carbonic liquid are present, indicating that this must be a situation where the fluid had appreciable concentration of carbon dioxide, which we will be discussing. They may also occur as monophase conditions, only a liquid or a vapor. So here are some real photographs from fluid inclusions as they are observed in host minerals. This is an example of aqueous biphase inclusion, where the vapor and the liquid are labeled as V and L, and you could see from the micron bar, which is 20 micron, and you can imagine what could be the maximum dimension of this. And what I mean by having a optical contrast with the host grain, you could see a very clearly demarcated boundary or the wall, inclusion wall, within which the inclusion is present. And this is an example of a mixed inclusion, where it is a liquid water, liquid carbon dioxide and carbon dioxide vapor. The significance of these inclusions will be discussed in the course of this discussion. So then let us see what are the host minerals in which we see the minerals. In fact, any mineral that is crystallizing from a fluid is likely to trap the inclusion. Only it is our capability to see the inclusions under the microscope in which kind of light, because we know that there are sulfide minerals or oxide minerals, ore minerals, which are opaque to normal visible range of the light, whereas the silicate minerals like quartz or carbonate like calcite or fluorite, apatite kind of gangue minerals, sometimes they are even observable in many other gangue minerals, but the majority of the fluid inclusion work is actually on quartz, which is a ubiquitous host in many of the ore deposits, in oxide and sulfide deposits as we see them. So 90% of the fluid inclusion work are on quartz. Other host minerals are calcite, fluorite, apatite, rarely garnet, cordierite, scapolite, and so on. So as I pointed out, that these fluid inclusions could be in primary growth zones, could be as part of the random 3-dimensional network as I shown in the diagram. They could be on the heel fractures inside a single grain of the host, or these kind of fractures could be transgressing through many grains when the fracturing has taken place after the formation of the hydrothermal vein or the ore body. They are the transgranular heel fractures. So in these cases, when the minerals are present in primary growth zones or in part of the random 3-dimensional network, we call them as primary inclusions. And when they are present on linear arrays on the healed cracks or fractures traversing through many grains within the host minerals, we call them as the secondary inclusions. This is general terminology which we follow in fluid inclusion literature as primary and secondary, although it becomes sometimes not a very easy task to distinguish them. And the heel fractures inside a single grain of the host sometimes is we use a word as a pseudo secondary, because essentially it represents the fracture which is within the single grain of the host mineral, which is not transgressed through through the entire body of the quartz vein or the ore body. There we use a word as pseudo secondary. Otherwise, the broad classification of the inclusions to primary and secondary is having a connotation of time, that the primary inclusions which formed during the growth or during the formation of the host mineral, and the secondary inclusions formed any time afterwards. So we study them in the laboratory by using doubly polished thin sections of a certain thickness, because these inclusions are several tens of microns in dimension. So, the thickness of the section should be at least 4-5 times the maximum dimension expected. So, generally they are 200 to 300 micron in thickness. We study them under the microscope at high magnification, and then we do an experiment which is essentially we call as microthermometry and other non-destructive analysis. Sometimes we can do some destructive analysis by opening the inclusions or taking the sample, taking the inclusion fluid out of the host mineral and analyzing them using many sophisticated analytical equipment. We will be discussing about the microthermometric technique, which provides the most fundamental and the first level information on these fluid inclusions. So, before we look into the fluid inclusion exercise and the data that we retrieve from them, let us first see the assumptions that we make before we proceed on to study the fluid inclusions. That the inclusions behave as closed system since the entrapment. There is no loss or gain of any component with the surrounding within the host mineral, and the inclusions behave as a closed system and have followed a constant density, constant volume, constant composition path, which we call as a isochore, and inclusions are trapped essentially from a homogeneous fluid, and the entrapment process is essentially homogeneous. So, the figures that I showed you here, this figure essentially whatever is where we are seeing them as heterogeneous assemblies, but these all are the post entrapment phase changes that we see in these inclusions, rather than the inclusion being trapped in this condition. The entrapment is essentially homogeneous, and the fluid, the entrapment is from a homogeneous fluid, and also the entrapment process is homogeneous. We will be able to explain the formation of these fluid inclusions in a very simple manner here. What I could see here, so this is a unary phase diagram of water. Here is the critical point corresponding to 374 degrees centigrade and 220 bar. So, this is the vapor stability field, this is the liquid water stability field. Let us assume that there is a temperature and pressure conditions to P1 and T1 where this mineral precipitated from a fluid on a fracture or any rock that is in the subsurface, and when this mineral is once it is trapped, it is behaving as a constant density, constant composition system without any exchange of component with the host mineral, and then the condition at which we are seeing them in the laboratory is different from the condition where it was entrapped. And since the path that it follows is an isochoric path, that means a constant slope dp by dt path. So, it follows a straight line path with the decrease in pressure and temperature conditions, with larger decrease in pressure with smaller decrease in temperature, and it evolves in the same one phase condition without undergoing any phase change till it reaches a point here which corresponds to the boiling curve of pure water. So, here the liquid and vapor. So, this curve corresponds to the liquid vapor coexistence, or which we call as a boiling curve, and when it intersects the point here, a small vapor bubble nucleates from this within this inclusion cavity. This can be explained on the basis of the differential contraction of the host mineral and the liquid, because liquid has got a higher coefficient of thermal expansion than the host solid, or it could also be explained on the purely on the basis of this phase diagram, that as and when it intersects the point here, the vapor bubble gets nucleated and it comes into existence. So, from a homogeneous entrapped condition, now it attains a heterogeneous state with a liquid plus vapor. Any further decrease in the pressure and temperature would make it move on this boiling curve, because it can't leave the boiling curve as long as the vapor and liquid are coexisting, and with further decrease in the pressure and temperature will only result in an enlargement of this originally trapped tiny bubble till the point it reaches here corresponding to the room temperature where we are observing it, where we see that this inclusion is the way we see there is a vapor and a liquid. So, this is how we can explain the entrapment process of fluids during the mineralization process, and assuming that the host mineral which was precipitating here was also precipitating along with our ore minerals, and that represents the thermal characteristics as well as the chemical characteristics of the ore fluid during the mineralization. So, this is entrapment condition. So, what this diagram, how we can use this diagram in retrieving the temperature. So, considering the fact that this happens in a process of entrapment like in the way we have depicted, if we reverse the process, for example, if we heat this particular inclusion while observing under the microscope by using our appropriate devices, which I will not be discussing here for the sake of brevity, and so what exactly is expected here is that as we increase the temperature, this is also going to follow the same path which it followed during the time of its entrapment and post entrapment phase change. So, the vapor bubble will gradually grow smaller and smaller and smaller, and till the time that it reaches the point here where the vapor bubble is going to disappear, and it is supposed to follow the same further heating, it is supposed to follow the same isochoric path. So, the temperature at which the fluid becomes homogeneous from this condition to a point here where the vapor bubble will disappear, we will call this temperature as the temperature of homogenization. That means, from a heterogeneous condition the inclusion attains a homogeneous condition, and so that we call it as a temperature of homogenization. Any further increase in temperature will make the inclusion follow this particular steep isochoric path, and then when we further increase, we do not have any constraint to reach at P1 T1. So, there is the limitation. So, the temperature corresponding to T1, if we drop the perpendicular over here, this should be the temperature of trapping or the temperature of formation of the particular inclusion. We say that it is the temperature of homogenization, or TH, and that is corresponding to the point at which the vapor bubble disappears, and temperature of entrapment or temperature of trapping, which we represent as TT. And so, here actually what we are representing here, that if we drop a perpendicular from here, this will be the temperature of homogenization, that is TH, and if we drop a perpendicular from here, it will intersect the abscissa on the point which will be TT, and there will be some difference of the temperature between the TH and TT. So, if we are relying on only this experiment, then we will be missing the temperature of formation or the temperature of trapping by a few degrees, and it all depends on the slope of this isochore will tell as to how much by how much we will be missing the actual temperature of formation. Here, if we have any independent consideration of temperature or pressure, for example, if we are carrying out this fluid inclusion exercise on a particular mineral which itself can indicate pressure, like sphalerite, whose composition is a function of pressure. Mole percent of sphalerite under certain conditions is sensitive to pressure, and the pressure could be determined. And if we are doing this fluid inclusion exercise on a mineral like sphalerite or any other mineral for that matter which can indicate pressure, then we have a constraint to stop here or to get this particular point of pressure of trapping, and from which we can drop a perpendicular on the x-axis to get the temperature of trapping. So, this is the story of a single fluid inclusion, and we actually measure innumerable number of such inclusions in an ore body to get a range of temperature for the formation for the mineralization process. That gives us a. So, first of all, when we talk about the fluid source, and we have characterized the different fluid sources like meteoric, magmatic, metamorphic, juvenile and so on, we can get some first-hand information as to what kind of a fluid we are essentially dealing with by the time we are finishing the microthermometry exercise on a large number of inclusions on the minerals that we have taken from an ore body. This is a very simple diagram, but fluid, crustal fluid is very complex mixture, like if we see this table, this gives us some idea about the general chemical characteristics of hydrothermal fluid. We see that it actually represents a whole spectrum. So, where the concentration of a chloride ion can go from 0.03 to greater than 7 moles per kg, sulphate 10 to the power minus 10 to 0.3, sulphide, NH3, carbonate, acetate, propionate, oxalate, malonate. This is giving it is of course not exhaustive list of the chemical species that could be present in a hydrothermal fluid, but it is a very complex mixture of many dissolved solids, anions and cations, and this gives us an idea, and from that we can know that what kind of what considerations we have to take when we actually are dealing with the actual real hydrothermal fluid, which is a much complex brine and complex mixture of many different phases, and we have to understand the phase relations in many such systems, and from that we can interpret our data on the thermometry. The characteristics of the hydrothermal fluid in terms of the source, we also characterize by their salinity, and as we saw just on the table that chloride constitutes the dominant anion in many of the hydrothermal fluids that we sample in different types of deposits. These diagrams, this figure gives a very crude idea as to how we can estimate the salinity in terms of the total dissolved solid of any hydrothermal fluid which is sampled from the fluid inclusions in minerals. Similarly, we can the way we conduct the heating experiments, we can also conduct the freezing or the cooling experiments and use very simple principles of colligative property of depression and freezing point to constrain the salinity, or in terms of which is expressed as the weight percent equivalent of NaCl. Here it is a part of a phase diagram of water and NaCl binary, where you can see the temperature at which pure water freezes at 0 degree centigrade, and this particular co-tectic curve represents the depression in the freezing point of water with increasing content in sodium chloride, and on a binary this temperature represents the eutectic temperature corresponding to 23.3 weight percent of NaCl and minus 20.8 degrees Celsius, and on the NaCl rich side this co-tectic represents the so this co-tectic essentially represents the ice plus liquid curve, in which with the decreasing in temperature the liquid becomes richer or more concentrated with respect to sodium chloride, and as and when the point eutectic E is reached, the solid which is your sodium chloride plus 2H2O, that is hydrohalite, will form along with ice, and if it is on the NaCl rich side, then it is already forming ice, hydrohalite plus liquid, and the liquid is becoming less and less concentrated with respect to NaCl, and when it reaches the eutectic temperature, both hydrohalite and ice crystallize. And if we consider the liquid which are essentially undersaturated or not saturated with sodium chloride, like the example which you took just before while discussing the heating experiment. So, we can do the experiment and freeze the inclusion and see at what temperature the ice melts, and we will be able to find out what percentage or what weight percent of sodium chloride, equivalent amount of sodium chloride will cause that depression in the freezing point, and we can determine the salinity of this fluid. So, likewise we determine the salinity of a huge large number of inclusions, aqueous inclusions which are present in the host minerals. The host minerals could be quartz or any other host mineral, or even sometimes it is also possible with some specialized techniques to study the fluid inclusions in opaque minerals also, and can retrieve such information on the salinity and temperature characteristics of the fluid as constraint from this fluid inclusion study. We can represent the data, because this is just for a example, because we once we measure a huge population of such inclusions, we get ranges of temperature, and we would like to plot them or represent or present them on a statistical, making us some statistical sense, and we plot them as histograms, and then find out that whether this fluid is essentially is coming from a one such population or coming from more than one population with modes or the temperature maxima more than one. So, this also gives us some preliminary idea about the process that is involved. And if you remember, we in one of our previous discussions we saw that this hydrothermal mineralization process, even though we identified many different fluid components, but the process sometimes involves involvement of more than one fluid types, and it happens because of fluid mixing process, as we will be discussing in a short while. So, this is the way we can represent the fluid inclusion microthermometric data. This is a diagram on which it is shown that the homogenization that we get could be of two different modes. The homogenization could be of the liquid phase or could be to the vapor phase. For example, if the inclusion initially or the fluid was initially in a vapor state, then any inclusion which is trapped over here will essentially be trapping a vapor, and with decrease in temperature, that vapor rich inclusion will give rise to liquid, and only difference will be that if it is a vapor phase, entrapment, then we will only be getting an inclusion where we will be getting a large vapor bubble as compared to in a liquid phase entrapment when we get a small vapor bubble. So, in such kind of a situation here, what the homogenization behavior in this case is L plus V to L. In this case it becomes L plus V to V, or we call as vapor phase homogenization. Here it is liquid phase homogenization. So, this is essentially the figure here is which is not shown here, but could be if the entrapment of the inclusion was in this field, then the homogenization also will be to the vapor, and the isocores will be in the vapor region. And here what exactly we mean, that if we get some such situations of which I will be discussing in a little while in the next class, that there could be vapor phase homogenization, and we would like to represent what is the proportion or what is the statistically how many inclusions were homogenized into liquid phase, or how many to the vapor phase, and what temperature range, to decipher something very important in that respect. So, this in the context of the aqueous fluid, this diagram which is constructed from a good number of or a substantial number or adequate number of fluid inclusions, where the microthermometric study has been conducted. They are plotted on a temperature versus salinity diagram, which we essentially call as a fluid evolution diagram. So, if we take a hypothetical fluid representing hypothetical fluid over here, then we can have several possibilities when we plot the temperature versus salinity data. That means the inclusions on which we have measured the temperature, and also we have measured the salinity in terms of weight percent NaCl equivalent. We can plot them as scatter diagrams, and depending on the nature of those scatter points, we get certain well defined trends. So, this trend is shown here on the horizontal arrows. Could be that there could be the mixing of different mix of fluids of different salinity. This particular trend would be for boiling, this could be for cooling, and this also could be for mixing. So, mixing of fluids, boiling of the parent fluid, and cooling or some such processes are very important from the mineralization process point of view, and it's actually in addition to the characteristics of the ore fluid, it also is very important to know that how the fluid actually evolved, because that actually caused the process of deposition of the minerals, which we'll see them which we'll continue discussing in the next class. Thank you.